All right, so our visual system has figured out what things in the world seem to represent objects, and perhaps it's even been able to recognize what those given objects are. The next problem it faces, or I should say a problem that it's simultaneously solving, is where those objects are. And there's some really cool things about why we have two eyes and what two eyes do for us in that regard that I really want to make the subject of this lecture. All right, let's do it. So week 3, lecture 5, perceiving where. I start off here with just this example to try to get you to realize how impressive, again, we are in some regards without maybe always appreciating it. If we, think of somebody playing baseball and hundreds of feet away, somebody hits a ball, the outfielders almost immediately seem to have a sense of where that ball will end up. By watching a little bit of its trajectory, they start to adjust and run back or run forward, and ultimately they're able to zero right in on where the ball is going to land, and they're able to perform fantastic catches like this little guy right here is. And so the question really is, how do we do this? It's like we're able to calculate trajectory physics somehow without even knowing what the formulas are. Well, let me kind of go a little slow and begin by saying we can do a lot with one eye. That's why I call this For You Pirates. In fact, when I talk about this issue in class, one of the things that I do, and that I suggest you maybe try, is I will throw something back and forth with another student in front of the class. And we will do that for a while with two eyes, both eyes open, and we'll ask everybody to watch how relatively graceful we are, how adept we are at catching these things quite easily. And then we'll close one eye. And what you see is that when you close one eye, you can still do it. You can still figure out where an object is. That is, you can still perceive depth, because that's what we're really talking about here. Where is that in the world? How deep, how far away from me is it? So you can still do that with one eye, but you cannot do it as well. Okay, so you tend to see the gracefulness disappear, and suddenly, people are making jerky movements to try to catch the ball, and they're missing a lot more often. So, give that a try, and then ask yourself, okay, so why two eyes? What does that extra eye do for me? Okay, well, here's the things we're using with one eye. We're using things like perspective. So we have some sense of how big people are relative to other things in the scene. This woman behind here is actually, if you cut her out and copied her and pasted her right beside the guy, this is what you would get. And so, really the image that she's casting is very small relative to the image that he's casting on our retinas. But our brain knows what size humans should be. So how it interprets this is that unless we stick her right beside him like this, where it's awful hard to perceive her far away, if we can provide some environmental support that she might be further back, then that's how the brain perceives it. So in the normal situation, we see her as, maybe a little shorter than him, but probably not much shorter, just very far away relative to us. So we use things like perspective, which incorporates knowledge and memory. And that helps us know how far away it is. So we can imagine if we're throwing a ball back and forth, the image that ball casts on our retina is actually getting bigger and bigger and bigger and bigger and bigger as it comes towards our eye. And we can detect that, and we translate that, not that the ball is getting larger, but rather that it's coming closer. So we use things like perspective all the time. There's other things that change as well with depth. For example, if you look at these rocks, you'll see the size of them. This is the perspective thing again. These rocks look really big. The ones over here look much smaller, but again, we don't really think they're much smaller. We think they're just further away. But we also have a lot more detail. If you look at the close ones, you see a lot more detail on closer objects, a lot less detail on further objects. And as you go further and further back, the mountains almost smooth out quite a bit. So we use that, how granular, how coarse or smooth something is, that gives us an idea of depth. Of course, we use things like interposition. So we know that this rock is in front of this rock because it's literally occluding this rock. Okay, we can see more of this rock than we can of, say, this one or this one, and that tells us that this one is in front. So we have all of these things that work just as well with one eye as they do with two eyes. We have one more that I want to show you because I think it's really cool, and that's shading, and it makes a really important point. So look at, first of all, this figure on the left, and what you see is really these balls are positioned in the exact same position relative to the grid underneath it. And if you're not convinced of that, check out this top one and notice that there's about 2 and a bit squares. There's about 2 and a bit squares here. Okay, they're really the same. All we've changed in these figures is where the shadow lies. Does it lie right underneath the ball, or does it progressively become further underneath the ball? So that's what's changing across these images, but what we perceive as changing is where these balls are. Suddenly, these ones seem to be going up, but staying the same distance from us. So this one isn't any further from us than this one, it's just higher in the air. Whereas in A, we perceive these as gradually getting further and further from us, receding in the distance. So let's think about this a little bit. Shadow. What's that come from? Well, it comes from the sun, the world we live in, what we're used to seeing. So the critical point being here, we have learned certain regularities of the world that tip us off to where things are, and we've kind of incorporated those now into our perceptual system so that we can kind of reverse engineer things. And by looking at things like shadow, we can figure out where things are. Let me show you a very dramatic example of this. So look at this first, and actually I'm going to leave PowerPoint, which is never as easy as I want from here. So I'm going to go really fast into the future. Oh, seems to be the only way I can do this. Okay, so here's this slide that I was just showing you. Let me make this a little bigger. Now, when you look at this slide, what do you see? You should see 1, 2, 3, 4, 5, 6. 6 of these should feel convex. That is, they curve out towards you, whereas the rest should seem concave. They curve away from you. They go into the distance. But look what happens. So this is not magic. Okay, take a good look at what you see. 6 popping out, the rest blending in. I am now just going to take this object and I'm going to spin it around until I put it upside down. And now watch what happens. Boom. Did you feel that? These 6 that were popping out are now concave. The rest feel convex. They feel like they're coming out towards us. Let me put it back. And there you go. There's the reverse. When we put it back, we now see that 6 of them are coming out towards us and the rest are going away from us. So this is one of these illusions of depth. And well, it's not really an illusion. It's really just how our system is working. Why is it working this way? Well, we live in a world where the sun is above us. And so think of a cave. If the sun is above us and shining into the mouth of a cave, what do you see? Well, you see shadow across the top and then brightness across the bottom where the sun is able to hit and penetrate. But if you have something convex, the reverse is true. You see light, think of a bowl. You see light hitting the top where it's bowing out and then a shadow underneath because the bowl comes out and casts a shadow underneath it. So this is just the way concave and convex things work in the world. But now when we see something that's two-dimensional but shaded in just the right way, we see it as concave or convex. And we can completely flip that perception literally by flipping the figure, and everything changes. You might ask, well, what if we just did this then? What if we just moved 90 degrees? Well, what do you see? It's kind of somewhere weirdly in the middle. It looks, if you think of the light sources coming over from where my cursor is here, then it looks like these ones are bowed out and these ones are bowed in. But if you think of the light sources coming from over here, then the opposite. So you can almost, this almost becomes a Necker cube of a sort, where you can see it one way or the other. But as soon as we put it in a way consistent with the environment, then boom, we tend to see it in a very certain and specific way. So pretty cool. And this is all a one eye thing. Yeah. Okay, so let's go on to two eyes then. Why two eyes? Well, really, what two eyes give us is much better, a much more detailed ability to perceive depth. And they do it in two ways simultaneously. One that maybe we don't appreciate, but one that we really don't appreciate. Here's the first one, convergence. Basically, our eyes will turn in to see an object, right? And the closer the object is to us, the more they turn in. A further object is further away. So we have these little muscles that detect that, and these muscles literally send signals to our brain, and our brain can interpret that. That if the eyes are locked on something, and if they have a very large angle here between them, which means they're really pointed this way, then whatever they're locked on is pretty close. But if the angle is smaller, then whatever they're locked on is pretty far away. So, just from how the eyes are tilted, we have a very powerful, useful signal about the distance of the thing we're looking at. Okay, now I want to draw this distinction. Okay, so we know where that is. It's almost like one of these golf things where you can detect how far the hole is. We know how far the thing is that we're looking at, but it's got things around it. Some of the things around it are closer to us, some are further away. What would be really cool is not only to know where that thing is, but to know where it is with respect to the things around it. We can do that too. That's what our two eyes do. Now this one, I hope, will kind of blow your mind. I want to start by just convincing you that something occurs, which is occurring all the time, but we're not noticing it. And it's very cool. So here's what you have to do. Take your fingers, just like that demo shows, but now focus your attention on the front finger, the knuckle, and keep your attention focused on that. And then move your back finger away or back towards the first one. So move this away and back to, but keep looking at the front one. And what you will clearly see is that you do not have one finger further away from you, you have two. And the amount that you have two, the distance between those two gets bigger the further you move that finger away from you. So you can see that, when I'm looking at the front figure, the back one actually produces two images. And the distance between those images depend on how far away that one is from the thing I'm looking at. That's something called binocular disparity. And so just to make this figure make sense, if we're looking at the red thing, now imagine these other things are positions of your finger, but imagine we could actually, go in front too. Well, the thing you're looking at, that locks into something called the fovea, the center of the eye. Remember where all the cones are, where all the detailed information is going. But the other thing, as it goes further away, say the purple versus the yellow, if you look at how far away the purple image is from the fovea versus the yellow, you see that the yellow is further away. That's exactly what we're seeing, that the second image is getting further and further apart. And so the eye can detect this, the disparity of everything else, everything we're not looking directly at, causes two images. We don't see that. I don't know why we don't see that, but we don't. We feel like we just see the one image of what we're looking at, but everything else is casting two, and the distance between the pair of images depends on how far they are away from the thing we're looking at. So that means when we have a scene like this, let's say we're looking at this gentleman. Well, we're only going to see one of him. We're going to see him very clearly because his image is on the fovea, and convergence will give us a good sense of how close or far away from us he is. But now everything else in the scene, everything, is now casting two images on our retina that do not fall on the exact same retina of each eye, and the distance between those, the disparity, is greater the further they are from what we're looking at. So if we're looking at him, we'll have two images of this guy, but they won't be too far apart. But this guy will have images that are further apart, and this guy will have images that are further apart still. And so with two eyes, we get this really rich notion of the scene we're looking at, the specific thing we're looking at, and everything around it. And so we get this spatially rich vision of the world that tells us where objects are. Now, where versus what? I've kind of separated that. Let's think back to the brain. What part of the brain does the what part of visual processing? That's the occipital lobe. What part does the where, the spatial where things are in the world? That was the parietal lobe. So literally there seem to be, and there's now growing evidence that there are two distinct visual pathways. That one pathway is trying to figure out what you're looking at, and another pathway is trying to figure out where you're looking at. And then eventually that information is brought together to give us the rich perception that we get. And we get this, naturally and very quickly. Just boom. We look out at the world, we see things, and we know where they are. Very cool. Okay. Of course, the story follows for other senses as well. Auditory perception, we also have a sense of where sounds are emanating from. But I'm giving you vision here to give you that, one rich example. Okay, so here's some things to follow up from. First, I think these are interesting for a couple of reasons. There's some interesting studies about babies and how genetic versus learned depth perception is. So we use something called a visual cliff. And you can tell that even very young babies are sensitive already to depth, not death. Depth, sorry. So check those out. If you're a technically minded person, here's a little video about how they're trying to do some of these in robots. And one of the things that I always appreciate is how hard they have to work to produce some robot model of vision that comes anywhere near as close to what we can do naturally. And this one I think you should check out. It's called Alice in Wonderland syndrome. One of the things our perceptual system is doing for us is giving us a really constant image of what's in the world. But people who have this syndrome, their perceptual systems are a little messed up, and their perception of objects where they are keeps shifting, and so they see things growing bigger and smaller and stretching, and which is to some extent more the reality of the situation. As we just move our heads, everything in the world, the amount of retina it takes up is changing. But our brain is somehow able to turn that all into a stable percept. Theirs goes wrong somewhere. So check that out. I think that'll also make you appreciate things. Here's a Wikipedia entry about that what versus where distinction I've highlighted. And if you want to test your own depth perception, here's a very simple depth perception test. Okay, so now we've kind of gone through the basics of at least visual perception, and now we're going to get into some higher level issues about attention and consciousness. And that's what we'll wrap up the week with. All right, so I'll see you in the next lecture. Have a great day. Bye-bye.